Very good morning. Welcome back to the second, you can say, example on robot kinematics. So again, I mentioned this is based on the request come from the students. So I'm just giving a little more detail about how to fix a frame and how to obtain DH parameter. Then we can see how to obtain the forward and inverse kinematic model. So last class we took a very simple manipulator called SCARA. So here also we'll be taking one of the simplest, so which is we call articulated manipulator. So we'll see how that goes, and as I already mentioned, we will go little complicated in the upcoming sessions. So let us actually move forward. We will actually see. So the example 2, which is actually based on 3R robotic manipulator configuration. So we will see frame arrangement, DH parameter, how to obtain transformation matrix, and we'll see how to obtain forward and inverse kinematic model. Okay, so you can see this is the 3R serial manipulator. So you can see the first joint is actually vertically rotating, and as well as you can see there are two R which are parallel. So that's why you can see R perpendicular to 2R parallel configuration. So now you can see that this is the first rotary joint which is having theta 1, and this is the second rotary joint which is actually theta 2 and theta 3. And we are actually looking at what is this point which you call nth frame, and you are actually trying to see what is this is 0th frame. So in the sense we are trying to address this configuration. This is what you call forward kinematic model, and later on we'll see that based on that how to find out theta 1, theta 2, theta 3 for given, you can say, task space or operational space variable. So since it is 3D of system, and this is the major axis system, so in the sense this theta 1, theta 2, theta 3 can be obtained with respect to px, py, pz. So in the sense if I write px, py, pz in the function of, you can say, theta 1, theta 2, theta 3, that is what I call forward kinematics. And if I actually know this and I try to find out theta 1, theta 2, theta 3, that is what you call inverse kinematics in this case. Okay, so let us move forward. So I'll actually show this is the case. So you can see that this is a given configuration. So obviously you can see this is the base and this is the end. So as usual we will actually start the, you can say, line diagram. So you can see, so the line says like this, right? So this is the first line and second line, and you can see third line. This is what I did. So now there are 4 nodes, but we will see what are the nodes later on. Right now we will actually fix the joint axis. So for the fixing joint axis, what we have seen, anything joint, the joint axis belongs to z axis. You can see this is z1 direction, okay, and this is z2 direction based on the given configuration. This is z3 configuration, okay, direction. So further we don't know what is z0 and what is you can say 4. So I am taking the convenient, so I am taking z0 like this and z4 also like this. So now it is actually very clear. So you can see that there is an intersection. So this is supposed to be one node, and this is actually parallel. If you see the common normal between these two, this is the line. So this is another point, and similarly this is another point. Since we are starting with a base, so this is another point. So in the sense I start 0 here and 4 here, and this is 3 here, and obviously 1 and 2 associated here. So in the sense you can see this is z1 and this is z2 and this is z3 and this is z4 and this is z0. So now what else you need to do? So you can see this is what we did first, and z1, z2 and z3 and z4 and z0 we have fixed. So now what else we need to do? They have to fix the x-axis. I made the configuration such a way that x-axis is easy. So you see z0 and z1 is actually parallel, so that x0 can be 2 other orthogonal axes. I will be taking parallel to the, you can say, longitudinal plane or longitudinal axis. So this is what I am calling x0, because x0 supposed to be refer with z0 and z1. In this case these two are parallel and same line, so there is no, you can say, common normal required, but the common normal direction is actually two you can say side. So one is actually x0, the other one is you will take y0 here. So now when you are talking about x1, so x1 you can see that this would be relation with z1 and z2, So in this case, this is the plane consists. So obviously, so x1 will coming out of the, you can say, this plane that can go inside or coming outside. I am taking the progressing side because the linked length cannot be, you can see, negative. That's why we are actually like taking x1 in this direction. And you can see z3 and z2 are parallel and the common normal is in this direction, so x2 also on the same line. So and x4, so z3 and z4 are parallel, so the common normal here, and the direction progressing side I take x3 and keeping x4 is parallel to x0. Okay, so that's what we did. Now you can see these are the frames. Okay, and this is the x-axis. You can see x0, x1, 2, x3 and x4 we have fixed, right? So once these all fixed, what is the next thing? Next thing is actually like finding DH parameter. So you can see the first you can say axis or first frame. The first frame is actually like you can see distance along x-axis, sorry, z-axis, that is 1, and remaining everything is same. So in the sense alpha naught is actually like 0 because these two are parallel with respect to x naught, and there is no distance along x naught, so that is 0, and this is the active joint, so that is theta 1, and you can see that there is a distance along z1, that is d1, right? So that is what we did. So now coming to the second frame, you can see second frame there is no distance because 1 and 2 are same. So in the sense you can see these two you can directly put 0. But what one can see, so z1 and z2 are actually like orthogonal, in the sense it is actually like a perpendicular. When you are rotating about x1, you can see that this is actually like rotated, so 270 degree. So in the sense alpha 1 is 270 degree, and you know this is actually like active joint, so that is actually like theta 2. Okay, so that's what we are actually like done. We have written in the radians, so that's why 3 pi by 2, right? So similarly we go the third one. You can see these two are parallel, so alpha 2 is 0, and you can see that along x2 there is a distance, so that is a2, I call this a2, and this is again active joint, so that is actually like theta 3. Okay, and you can see that there is no distance along z3, so this is 0, right? So that is what we did. And then the final one is actually like you can see straightforward. These two are actually like parallel, and the common normal is along x3. So in the sense you can see alpha 3 is 0 and a3 is exists, and this is actually like passive joint, so theta 3 is 0 and there is no distance. So that's what we can see, right? So now we have obtained the DH parameter. I hope you will not be having any issue in finding this. So let us move the, you can say, transformation matrix. I am using the non-standard one. So now you can actually like substitute these DH parameter into this you can say individual transformation matrix, and you obtain individually. So T01, T12, T23 and T34, and now you obtain all those things. Now you can actually like see this is the frame arrangement and this is the DH parameter, and we will actually like multiply T04, which is actually like T01, T12, T23, T34, right? So now I am actually like multiplied and I am using it, that relation finally. So this is what you call the final transformation matrix of 4 with respect to 0. Now I already told whenever you obtain this, you have to cross check with the home position. So here home position is all thetas are actually like 0, because these are the active joint, all three are 0. If I actually like take it all 0, so what would be x? So x would be simply a2 plus a3, because this is a2 and this is a3. What would be y? Y would be 0 and z would be simply d1. We can check. So I substitute this is 0, so this become 1, this become 1, this also become 1. So a2 plus a3. So in this case this is 0 and this is 1 and 1, but 0 into anything, this becomes 0. And third thing is you can see d1 is physically present, and this becomes 0 and this also becomes 0. So in the sense this is d1. So you are getting this home position. So similarly the orientation you can see x4 is projected on x0. So in the sense it is actually like 1 0 0. So 1 0 0, and z4 is actually like projected on y. So in the sense that is actually like 0 1 0, right? And you can see the y is actually like projected opposite of z0. So in the sense 0 0, minus 1. So you can actually like check the home position by substituting theta 1, theta 2, theta 3. So this become 1, this becomes 0, this becomes 0, and this become actually like 1 into 0, so 0. This is actually like 0 into 0, 0, and this become minus 1, and this becomes 0, and this become 1 and 0. So you can see this is also uptime, right? So in the sense your DH parameter and the frame arrangement what you made, that is right, or you can say giving a proper result. Now we'll move forward. So this is what you call, this is a major axis system. So this is what you can call as a you call px, py, pz, and this is actually like major axis. This is actually like defined, these three defined with respect to theta 1, theta 2, theta 3. That is what you call forward kinematic model, so that you can uptime. Okay, so based on the forward kinematic model, what one can see, if px, py, pz is given, can I find theta 1, theta 2, theta 3? Yes. So theta 1 is straightforward. You take tan theta 1, that would be py by px. So in the sense, this is the tan theta 1, you can see, right? So you divide this divide by this, so you will get it. So now you can see these two are common, so this will go out, this will get, so that is what you get it, right? Similarly, theta 2 and theta 3. So if you are looking in the front plane, you can see that this is the you can say theta 2 and this is theta 3. The sense this is look like a 2R serial manipulator, and what one can see, so you can write px divided by cos theta 1 is actually like a2 cos theta 2 plus a3 cos theta 2 plus theta 3, right? And d1 minus pz, that would be a2 sin theta 2 plus a3 sin theta 2 plus theta 3, right? So what that obtain? So you can see that this is very similar to L1 C1 plus L2 C12 is actually like X. So Y is actually like L1 S1 plus L2 S12, the similar form, right? This is equivalent to Y and this is equivalent to X. Then you can use the same relation what we have obtained, that's what we have used. You can see theta 1 is straightforward, and theta 3 and theta 2 can be obtained with the same way. So you take the, you can say square and add, then you will get cos theta 3, then you know like sin theta 3 how to get, then you can get tan theta 3, and then for that what we are taking px by cos theta 1 as cx and cy is d1 minus pz. Once this is obtained, then you know this is the other relation, then you got it, right? So this is what we obtained as you can say forward and inverse kinematic model. So now I hope you are clear a little more how to fix the frame and what is the arrangement, all those things. So now if you have any questions you can post, otherwise we'll move forward with the 6 degree of freedom manipulators and all, some more example, and then we will actually close this particular, you can say, supplement sessions. Thank you. Bye.